Good morning, everybody, and welcome to yet another episode of the Python Comedy Hour. Today's topic is more on regression. More space on space, not the other interpretation of that. And it's a really good turnout. So I've waited a few more seconds. And while we're waiting, you'll have 2 laboratories due this week and a homework. And I'm not sure I've got the homework posted on the server. I'm not sure I got it all blackboarded yet. I'll work on that during lab, and I'll let Farhang know when it's ready to go. All right, so without any further, thanks, Abby. Oh, yeah, he's definitely bunking in a big way today. I thought I was sharing my screen and I didn't. There we go. So I have on the server, I'm going to work directly on the server. I know it'll probably crash partway through, and that'll be fun for everybody because then I'll have to reboot it. And then Farhang will take over and do his lab thing while we're waiting on rebooting. But the topic for today, which if we go through Blackboard, let me get to the home page and go to lesson. Make sure it's there. It should be. Let's make it available to you all. This might work better for everybody. Good thing I checked that. Lesson 19, regression continued. And when you click on it, it takes you to here, and we'll work on that. I'm going to go back to my copy. So what we'll be changing over the next hour is the contents of this notebook will change. So if you choose to download it now, it will be different than what's there at the end of the hour. The topic for today is multiple linear regression and weighted linear regression. Multiple linear regression is simply an extension of what we've already shown you that allows us to use other variables to make predictions. And I'm going to have to switch cameras because I need to write some things down. It's easier to me to write it by hand. So I'm going to switch to my down-looking camera, which is not even pointed right at all. Let's get that all located. I'll use this as a target. This picture is just so I can get the camera position right. You don't have to look at that scary thing anymore. You've already passed that exam. You've already gone through that exam. Okay, so that will give me working space. So if you recall, last time we looked at data models of the form y equals mx plus b. And then to get fancy, we chose different letters of the alphabet so that we could be uppity and cool. And so our y became beta 1x plus beta 0. And then we put the beta 0 in front of the beta 1x so it looked like y equals beta 0 plus beta 1x. And then we recalled that we have a whole bunch of different values of y. Different values of x. We have this beta 0, plus sign, beta 1, beta 1. So that's just 3, but it could be a lot more than 3. And then we applied principles of linear algebra that we learn in our linear algebra class. We replaced y with its vector equivalent. So the symbol I was using was y with an underscore to indicate that's a vector. So what does y, the vector, look like in this particular instance? I'll do the hard work. Remember, when you do vectors, you draw these columns around it. What goes in the top row of the y vector? Anybody, you can unmute yourself and make a flat out guess. If you're correct, I'll say yay. If you're wrong, I'll attempt to come up with some humiliating comment. Just kidding. Any guess is fair game. The right guess will be faster.
What's the question again?
What goes up on the first row of that y vector that I've drawn the picture of? It's currently full of nothing but nothing.
Y0.
Y. Okay, we'll start counting at 0. Good. What goes in the next row?
Y1.
In my example, I have how many things in it?
You have up to 2.
I got 3, so we'll go to y2. Okay, so good. Very good, everybody. That's what our y vector looks like. And as we were building this, you remember that we created a design matrix, which we called CapX. And then we had our parameter vector, which we called beta. So let's go ahead and build what CapX looks like. In this particular example, we have 2 coefficients, so there'll be 2 columns in CapX. What's the first column going to be comprised of?
X0.
I'm going to take some instructor liberty and put it here on the right side because you actually gave me the second column. What's the next row of the second column? Well, you're on a roll, man, so don't stop until you get it wrong.
So the next one, would it be X1?
Excellent. And I'm going to imagine you could come up with X2 all by yourself, no help. What goes in the first column? What would go to the left of it?
Are we allowed to do negative numbers?
We don't need negative numbers. Look at what the linear algebra is doing. It's taking a design matrix and it's going to multiply it by a coefficient vector. So what values in the design matrix have to be there so that when you multiply it by the coefficient vector beta 0 and beta 1, you recover beta zeros in the first column.
So is it x beta 0?
You need ones here. So
1 takes the place for P. For beta, I mean.
1 is, let's go ahead and finish everything out. So here's our beta vector. And when we do this in linear algebra, our formula looks like y equals, and we'll actually do the design matrix, 1, 1, 1, x0, x1, x2, beta 0, beta 1. And the result of that vector multiplication is beta 0 plus x0, beta 1, x0, beta 0 plus beta 1, x1, beta 0 plus beta 1, x2. So that was for a simple linear system. Going from this representation to the matrix vector representation is pretty straightforward. You can think of these columns as they are what multiplies the beta zeros and the beta ones. Now, in terms of this particular data model, we have one explanatory variable or one feature or one predictor variable. And the name of that predictor variable is? Give you a hint, it's what marks the spot. The name of that predictor variable is?
X.
X. Well, let's suppose X, or for a particular observed process, we have other variables that we're interested in using as predictors. So naturally we change colors to green. Let's suppose we also want to consider, let's see, X, Y, Z. I'm going to pick a variable called Q. And it will have its own multiplier on it, beta 2. So where would Q fit into this design matrix? This matrix here.
Wouldn't it fit in the middle of it?
You could put it there. Where's a more logical location? Imagine you can take this column and put it here in the middle where you suggested x0, x1, x2. And then Q can take those places, Q0, Q1, Q2. I'm not replacing stuff in the right column. Actually, I'm adding a new column to the design matrix. We had the original two columns, the column of ones, the column of x's, and now we're adding the column of q's. What happens to the coefficient matrix? If we've added a new column of predictors or estimators, what do we have to do to the coefficient matrix?
We need a new row for beta 2.
Correct? And that changes this. And now our model written back up in this form is y equals, oh, then maybe some of the difficulty was I was pointing to places that were not on the screen. A y equals beta 0 plus beta 1x plus beta 2q, where x and q are explanatory variables, exp. That's one of the names that's used. The other one is features. Older is predictor. And y is our observation, a response. And the whole equation itself represents our data model. So we're not constrained to just adding a single column. We can add as realistically as many columns as we're willing to pay computation time for. The only stipulation being, to use the process we've already studied, is that in the coefficient terms, the betas, the model has to be linear. So we could square the x if we wanted to, and that would be fine. We could cube the q, and that would be fine. We could take natural logs of q, as long as in the betas, those are all still linear combinations of the explanatory variables. That overall process generalized is called multiple linear regression or multiple least squares. So let me switch back to a different camera and keep that mess over here in case I need it again. Push that over there so it will fall on the ground. And we will continue with a fairly simple example. I'm borrowing material from our class textbook in chapter 15 called Prediction. And I put this, the URL that no one reads. Let's look at an example of multiple linear regression. So we'll take an example from the world of business. We're going to need pandas and NumPy and plotting capabilities and maybe Seaborn. So those all get fired in right now. And we're going to look at a file called e-commerce customers.csv. Let's go look at the file in its somewhat native form. So we have an email for a bunch of customers. It's a small file, it's only 500 rows. We have an address. We have the color of their avatar. And we have what ultimately is useful information for our goal. We know how long they spend on our website. We know how long they spend in our app. And we have time on website, length of membership. So this is our Facebook. And the most important number to us as revenue scavengers is how much money they spend in our in-app application. Our goal as a business we're a profit-making business, is to make the yearly spend as big as possible and adjust whatever feature over here we can to convince those people to make more of their money ours. I could do a fairly cynical current affairs comment on that, but I think I'll keep my mouth shut for risk of losing my job. So let's look at the variables we have. We have session length, time on the application, time on website, length of membership, and the yearly spend. Let's see what we can learn with multiple linear regression. While we're still here in the spreadsheet, this person spent $500, and let's get one of the big ones. Here's a $700 spender. Does it appear, just looking at those two instances, that the length of membership has an impact on how much our customers spend? Well, this person's been 4 years and they spent 587. This person's been almost 6 years and they spent 700. So as the number of years of membership goes up, they appear to spend more money. So we need to make people stay members longer or kick out all the new members. You would never do that in the world of business, because when you're stealing money left and right, you need to do it effectively. The time on website, if they spend 39 minutes, we have a single instance of $587, 37 minutes, $700. So it seems on those two instances that the less time they spend on the website, the more money they spend. That seems kind of counterintuitive. Time in the application being different than the website, 12 minutes and 12.89, very, very slight differences in application time. So we might conclude the application time doesn't give us much insight into how much they're going to spend. Average session length, 34 minutes, 34 minutes. The only thing in just those two instances that appears to have an influence on how much money is spent is the length of the membership. That's just looking at two instances. And we have 500 we would have to explore. So let's go ahead and read the data in and then examine the structure. So here's the various session lengths, yearly amounts spent. And we have a couple of tools at our disposal already. What might be one way to try to explore the relationship between dollars spent and some of these variables?
Okay.
Good. Yeah, we could plot it. That makes a lot of sense to me. I'm not going to do that just yet, but that's certainly an option. Actually, let's go ahead and do that, but I'm going to let you guys walk me through it. So how would I plot? This is clearly what kind of structure is it?
This data frame.
It's a data frame. So are there plotting routines already built into our friend Pandas or not?
Yes.
Well,
There are.
tell me what to type. Let's plot length of membership versus yearly amount spent.
Okay, I can't remember the exact syntax, but basically we need to first assign those two columns to their own lists.
Okay.
Or am I doing it a different way?
Anyone else have a suggestion? There's 30 of you. Someone knows how to do this.
Define a plotting function.
That's a hard way. Is there any way to do it in, let me go ahead and bring up the chat box. Maybe somebody suggested it there. Is this going to be explained in a lesson? That was probably a little while ago. So when you don't know how to do something, you go up here to the mighty GoogleNet, Pandas.
There's a way to do it, but isn't it where you
Let's just how to plot two columns of a Pandas data frame using points. So let's see if we get anything. Oh, we have this thing called data frame.plot. We give it the X value, the Y value, and lo and behold, maybe we'll get something. So let's go ahead and just copy this sucker, and then we will go ahead and
That's the one I was thinking about, if I forgot it.
so what should we put for our column name 1?
Yearly amount spent.
Well, I want the money to be on the up-down axis, so I'm going to use
Should we spend time on that? Because that's one we care about.
we'll just grab this first one first. Time on the application. I'm being careful to get the key names correctly, and then where's the spend? Yearly amount spent. So those I believe are the column names that are in the original data frame. And I don't want to copy and paste them from there because they'll probably bugger it up. Now we got to take care of these little itty bitty quotes that are in the way that are designed to make the pink screen of failure appear and make us make a judgment call on ourselves that's inaccurate, and we'll have it just do plus. So this is a no-brains plot. The x-axis will be time spent on the application. The y-axis will be yearly spend. Run it, and we get an error.
Don't you need to put ecom.plot?
That is probably a really good idea. Thank you. So there we go. So what do we see from this plot? You can use the fancy words that Farang taught you last week. Is there any evidence that time on the application has any impact whatsoever on the yearly spend?
It looks like
Seems to be a positive correlation between time on app and yearly amount spent.
Yeah, I would agree with that assessment. I probably look at these a little differently than you all. This is a blob to me, but because the corners of my plot are vacant and the middle part of the plot has dots in it, there is some evidence of correlation between time on the app and the amount spent. The other thing I look at is the scale of the up-down axis. I'm going from $300 to $700, and that could buy me a really nice trip to a place where I don't have to deal with customers. And anyone who's ever had to deal with customers understands the attractiveness of not having to deal with customers. Let's see if the session length has any impact on information. So I've copied the term average.session length, and I'm going to put it here. Rerun it, different plot. What do we learn from that?
The same thing.
Yeah, would you say that
it's good.
it's a better or worse explainer of yearly spend? This is looking more and more like a circle to me.
I'd say worse.
And so whether it's 30 minutes or 35 minutes, there's kind of this big blob in here. We might be just as good as guessing that the average spend is 500. Let's look at another one of our variable choices. Length of membership, which was the first one that we looked at when we were just looking at the table. So does length of membership appear to have any correlation?
Definitely.
That would be a yes. Length of membership looks good. So far, if you were to summarize the correlations, have they all been positive so far?
Yeah.
Yes.
Even if they're lousy, yes, they've all been positive. And time on the website is useless, which I knew ahead of time. Okay, so we could arbitrarily choose just to build a data model strictly on the length of membership, or we can say throwing away any data is bad. Let's instead build a model that considers all the explanatory variables, and then later on we can decide which, if any, variables to drop. So I have a second table, which is advertising. And in advertising, let's see what it looks like in its native form. It has daily time spent on a site, income, internet usage. Whether they clicked on the ad. So this is a tool that lets us associate time spent on the site with whether or not they clicked on the ad. I bet I don't actually use advertising. So I'm going to go ahead and suppress that because I actually haven't got to that part of it yet. So what we're going to do is we're going to examine the value of a data model that includes average session length, time on the app, time on the website, length of membership in predicting the yearly amount spent. So I'm going to do it using our linear solver. And so I'm just going to load that in from last time in a vector matrix multiplier. And now I'm going to create a few lists. This is me actually being lazy. You could probably do this without this particular activity. So I'm going to create a list name app time, session length, membership length, web time, and then the payment, which I've called Money Shot, based on a movie I saw this weekend about baseball. And so app time has time on the app. Session length is average session length, length of membership time. You can see the variables here. So we go ahead and create those lists. And now we're going to construct our design matrix. So our design matrix is going to contain a column of ones, and those column of ones correspond to whatever value we're going to obtain from our linear regression for the beta 0 coefficient. We're going to contain a column of the application times, which is going to be corresponding to the time spent on our application, session length, member length, how long I've been a member of the company, and finally the overall web time spent on our website. So our four explanatory variables are application time, session length, member length, web time, and our result output variable is what we called our yearly amount spent. And we're going to apply our ordinary least squares method to these 1, 2, 3, 4 predictor variables and 1 output variable to make a data model. So we do that, and either it's done or it's broken. And now we'll do the necessary linear algebra. We discussed this last time. And these are the coefficients. So this is beta 0, beta 1, beta 2, beta 3, and beta 4. And if we were to keep in mind the scaling, beta 4 corresponds to web time, and it's less than 1. So for every doubling of web time, we don't necessarily get a doubling of money spent. But if we look at the membership length, it has a value of 61. It's like 2 orders of magnitude bigger than the time spent on the web. So for every doubling, if you will, of membership length, we get 120 times more money spent. For every doubling of session length, we get 50 times more money spent. For every doubling of application time, 38, 40, almost 80 more dollars is spent, because these are going to be in units of dollars based on our model. So with that information, let's go ahead and make our function, our money spend function, based on application time, session length, member length, website time. And all we do here is now take our parameters that we have determined from our linear equation solver and put them into a function. So the value of money spent is minus 1051 plus 38 times application time plus 25 times session length plus 61 times member length plus 0.43 times website time. And there's just a function. And then we can use that. Let's go back to our plotting because we don't have any other reasonable way to assess our work yet. Let's go ahead and predict the spend based on web time. We'll make a nice plot. So what we're doing here is we're going to evaluate our predicted spend. We're going to assume everything else is at its mean value. At the mean value on the time of the application, mean value of session length, mean value of length of membership. We need the mean value of time on website and a standard deviation, and we're just going to plot plus and minus 3 standard deviations, and we'll make a plot. And we learn that if we vary from 34 to 40 minutes, that's 6 standard deviations of time on website, we get an increase of annual spending of a whopping $2. So that hardly justifies the time that we're going to charge the company for this fine marketing analysis.
Wait, how do you know it's $2?
Pardon?
How do you know it's $2?
Well, because at the left end, our data model tells us that if we spend 34 minutes on the website, there's $498 of annual spend. If we spend 40 minutes on the website, there's $500.50 of annual spend. So 500 minus 498 is $2.
Okay.
So let's look at some of the other variables. So what we have here is enough of a framework. If we were smart, we would put this into a function, but we're not that smart. Let's just change the name. Let's not change anything. I don't want to break it. I'm going to copy this, and instead we will call this our predictor. And what I want to do in this case is, let's do the one we know is going to work really good. We'll do length of membership next. So what we want to do is we want to copy here, and we want VARMEM. So I'm making up names. E-commerce. We tell it what critter we want. We want its standard deviation. And now we will just see varmem. We'll just change this word to mem. And everyone see why I'm doing it this way? Anyone have a clue why I'm doing it this way? No, naturally, complete silence.
Do you not want to like mess up do you not want to ruin basically the function you've made?
Yeah, I already have it working, so it seems easier just to change a few names and use something else that's working.
I do have a question. Why did you use standard deviation? Like point standard deviation.
Point STD, so I can get the number of standard deviations away from the mean value. It's just a way of estimating the range of information.
Oh.
I mean, I could have gone from 0 to 10,000, but I might have a whole lot of entries that that aren't useful. So I'm just picking a value that's close to the mean value to explore the behavior around the mean value. We've got 4 variables here. I can't visualize that in my mind. I suspect you can't either. You might be able with 4. P-R-E-D-I-C-T-O-R. And I'll go ahead and I'll leave that name alone. Okay, memory. And then I got to put this as AVG WEB. And the one I'm going to change is that. So notice what we've done here. We have not affected our data model whatsoever. It's unchanged. It's whatever it was when it was defined. The Only thing we're changing is our predicted spend from the data model, and we'll make a plot. And when we run this, we're going to get a straight line again, but let's see what we learn in the up-down axis relative to the left-right axis. We're no longer doing X label, Y label. Looks like somebody was being for sure there. We're no longer doing time on website in the x-axis. Our predictor is now what? What do we want to label this as?
Length of membership.
Yes.
I assume like years.
Member length years. Yeah, not ears, years. Okay, so we'll still get a straight line. What we're interested in is how much of a variation there is around the 6 standard deviations. Okay, so let's see, spend versus time, spend versus member length. Now we're learning something. Going from 1 to 6 years of membership length, we get an almost $300 increase in spend. And so you can argue that 6 standard deviations of member length is a whole lot more informative than 6 standard deviations of time spent on the website. And we could play that game with the remaining variables, and we could even put some effort into plotting the dots of the observations to see how well this straight line goes through those. I'll leave that for you all to do on your own time. You'll have examples from the labs. So that's multiple least squares. And that was rather trivial to simply take an ordinary least squares model in vector matrix form, so doing the linear algebra. And as we added variables, all we're doing is added columns to the design matrix. The actual work involved at that point is simply us hitting a return key. Another extension of multiple linear regression is something called weighted least squares. And what we've just done above, our design matrix, our equation that we solved looked like that. And if we were to put an identity matrix in, so that's 1s on the diagonals and 0s everywhere else, there's no change. In that case, the weight matrix is just the identity matrix. But we don't have to use a matrix that has 1s on the diagonal and 0s everywhere else. We can have a matrix that has non-zero off-diagonal terms. The matrix itself is called the correlation matrix, and it allows us to do things like account for data that are noisy, have a lot of variability in one part of our explanatory region, and less variability in another part of the explanatory region. Farang taught you a really fancy, weird sounding word for that case where you have variability that changes as you move to different parts of the plot. Anyone recall what that word is? Oh.
Is it association?
It's a weird sounding word. No, it's not association. What did we call a data cloud like this where the variability was the same anywhere in the cloud, where it didn't have that horn shape? Homoscedastic. So in this case, where that's the opposite of homoscedastic, what would be the word from your English language that you would use when it's not
Heteroscedastic.
heteroscedastic? Okay, so all that is a big fancy word that means that the variability in one part is different than the variability in the other part. By all means, use the fancy word when you're among people that are signing your paycheck, because then they'll feel they're getting their money's worth. When in fact, you're just dealing with the part where it's noisy in one part, not noisy in another part. In that case, what we can do is when we build the covariance matrix, we can consider the off-diagonal terms and actually use them as part of the regression. So I'll return back to a example that's taken from this document right here, which is a example to show weighted least squares estimation in a couple of different conditions. And we'll make a picture, and then I will hand you over to lab time. So you have a lot of time for lab today, which is intentional. So this first one just creates some imports some necessary tools, stats model, SciPy, NumPy, and there is a class called future, which is the print function, which it needs later on. And we're going to create a random seed. And by actually supplying a value for the random seed, this script will produce the exact same output on your computer as it does on mine. And now we're going to construct 2 samples with different standard deviations, if you will. And we will run a weighted least squares regression model. And this coefficient, x1 and the constant, those are the same as beta 0 and beta 1. And then when we generate the residuals, we can do that and fit them and generate a covariance matrix. And then it's also always nice to plot things. And so the plot is as follows. The blue dots represented our data, which in our case were fabricated. We made them using a script. And you notice that in this part, where the cursor is moving up and down, making you nauseous, I hope, it doesn't move up and down very far. And then we get off to the right, all of a sudden that up and down move starts to get larger. So the variability on the right side of this picture is larger than the variability on the left side of the picture. That is an example of, fancy word.
Heteroscedastic.
Good. Good. Prompting works. That's an example of heteroscedasticity. And if all these lines weren't in the way, confusing your eyes, it would kind of look like a horn. Probably just a trombone or a trumpet, but a horn of any kind. And the solid blue line is our, think of it, that's our generating function from which these data were constructed. So it has some slight curvature. The blue line's not a fit. There was a function that the blue line was used, and as we moved from left to right, it evaluated the function, recovered a numerical value, and then added onto it a random number, which is what creates the variability. And we designed it that as the function got over to about here, the potential size of that random addition was larger. That's how we generated heteroscedastic data. So this is one of those few instances where we have God privileges. The blue line is God. The blue dots are what happens when God hands down the information to the God information interpreters. And they add a little bit of their own interpretation to it. And that's how we get these off-axis lines. And then we go back as man, and we have to try to figure out what God was telling us. If we apply ordinary least squares technique, we would infer the red dashed line would be our data model, And the red dashed line, as a data model goes, isn't horrible, especially if we're over here on the left end. It would be reasonably accurate that we would interpret what God had told us. And as we get to the right end, where things get bigger, we see our data model isn't very good at what the true value is, and it's also not too good at guessing the estimates. If we were to also plot plus or minus 3 standard deviations of the predicted value, we get these red lines that are running parallel to our prediction equation. And what those plus or minus 3 standard deviations at any vertical slice produces is an interval estimate. And so, for example, Abby, you're going to get picked on because you're a good sport. Let's suppose that we were at a horizontal axis value of 10, and we're using our ordinary least squares predictor. What is your estimate of the value of the predictor at 95% confidence? That's plus and minus 3 standard deviations. Tell me what the interval is.
So you're making me look at 10, x equals 10.
X equals 10. I'll put the curve right in the middle there.
So our lower bound looks like it's going to be 8, I think. And then our upper bound looks like it's going to be like, looks like 9. I'm not too sure.
Let's see, 10.
Oh, are we looking at the dash lines too to determine our
The red
confidence?
ones. Yeah,
Okay.
you're not that far off. So at 10,
It's like,
I see around 7
yeah,
for the lower interval estimate and
11.
for the upper interval estimate. Okay, very good. Excellent. Now, if we apply the other technique of weighted least squares, where weighted least squares keeps track of the covariance as we do the fits and has the ability to render interval estimates that change depending on where we are in the data set. If I were to ask the same question, we would state that with 95% confidence, or our 6 standard deviation confidence interval of the estimate based on our weighted least squares is 8 to a little bit over 10. But if we move out here to say 17.5, the size of that interval increases to reflect the increased variability that we observed in the data. And the way weighted least squares achieves that is by creating a covariance matrix that considers where you are in the data set. If we look at the weighted least square regression results, we don't see much difference in the coefficient on the intercept and the coefficient on the explanatory variable. We have some internal statistics that are generated as part of the process and a warning to us. And we actually can perform t-tests on the individual coefficient estimates as we wish. And those are left for your laboratory. Okay, so let's do a quick reiteration. I'll hand you off to lab. Today we looked at multiple linear regression. The key point to that is it's no big deal to add more explanatory variables. You're not constrained with y equals mx plus b. It is by far the most common thing that appears in textbooks in the history of the world because at one time it was as complicated as was realistically capable. But then they invented this machine called the vacuum tube, which later on, solid state version of it got called the transistor, and then there was the integrated circuit, and then before you know it, you have the cell phone, and everything's off and running. And we have computational resources now that we didn't have then. And so we're not just constrained to y equals mx plus b. We can have multiple explanatory variables. We, the human being, however, in that instance, are responsible to determine the significance of individual explanatory variables, whether they're worth keeping around, such as time on website versus membership length. As you recall, membership length was a really good, solid predictor. I'm going to go ahead and put that back here in the picture to make my point, since it's being recorded. Length of membership has a pretty dramatic prediction value. We can't really teach a computer to do what we just did. A computer can calculate a correlation coefficient. It can perform some predetermined statistics on that and decide what variables are to be kept. But we, the human being, have to supply the insight that length of membership is a meaningful metric of our ability to make people spend money. Because it's quite possible we get a really strong correlation with a variable that makes absolutely no sense. Or we can always do the ultimate correlation. What do you think that's going to do?
I think
That-
I think that'll look good.
Is that going to, yeah, oh, it's going to get very angry at me.
Never mind. I was
I was expecting it to give me the tightest straight line imaginable. Let's see what the error is. That's cool. Key error. Did I do a spelling mistake or something? It does not like to plot on itself. That's actually quite funny.
just add another column, yearly amount spent also.
Yeah, but what I was expecting was a picture that looks like this, all based on the actual. There'd be 500 dots and they would line up in a beautiful straight line because money spent is a good predictor of money spent. Let me see if I can undo my mistake. Let's see, is Control Z. Oh, sweet, that works. There we go. We'll leave that be. We'll leave that as is. That would have been funny, but it should. I would have expected it to plot as pretty much just a bunch of dots. So we would have had 300 to 700 on this axis, 300 to 700 on that axis, and it would have been just a beautiful line marching from left to right. So that was the importance of multiple linear regression. And then we introduced some terminology, just words, for weighted least squares, where the covariance matrix becomes a significant contributor to the value of the prediction. And you'll see that in the next two labs to some extent. So I am going to save everything. Done. I am going to find Farang and make him the owner of the presentation. And
Since we have a good amount of time, we are going to give you a 10-minute break and we will begin the lab at 10:05.
11:05, right?
Yes, 11:05. Yes.
Are we taking questions?
Yes, yes.
Oh, okay. Dr. Cleveland, you mentioned you saw a baseball movie this weekend, and it's what you named your variable after. What movie was that?
Moneyball.
Moneyball.
Can you hear me?
It's
Hello?
Brad Pitt, right?
Yeah.
I wish.
No, I was talking about the movie. Go on, James. Ask your question.
No, it's okay. Sorry. You're good. Continue.
No, I mean, if you had a question, go on. We will hear it.
The question that I had was whenever it comes to the matrix, like the C matrix D vector equation, I'm still kind of confused whenever you put in the I and J variables, like where are they coming from exactly? Like it's in line, well, it's not line 47, but it's where it says 47 right there. Yeah, the copy A matrix into C matrix.
Okay. So you don't know where the I and J comes from?
Well, it's not necessarily just the I and J. It's like how they interact with the thing that we've been doing. into it. Like I don't understand how the A matrix goes into the new C matrix variable.
All right. Go back to my overhead, and for the time being, don't worry about the names A and C. So the matrices are constructed, they're another way of representing a collection of equations. Most of the time, I'm going to go ahead and speculate that in your other classes up to this point, even in physics, you probably haven't dealt with much more than 3 or 4 equations and 3 or 4 unknowns. We're not constrained to 3 or 4 in practice. We are constrained as human beings, and we can't visualize much more than 3. And so each equation in a vector matrix form formulates a row. Each variable in the equation identifies a column. And so we have to construct these matrices in order to perform this linear algebra. And what our linear algebra solver does is it performs the arithmetic equivalent of beta equals x transpose x inverse x transpose y. So that's all that the matrix equation is doing. Although in this particular representation, that is computationally really the hardest possible way.
I can't see the,
find answers.
can you push the page down a little? Thank you so much.
So that's what we're trying to accomplish. Now, the reason we have a C matrix and a D vector is our linear solver script that I chose to use, upon entry, assigns A to a value M and then starts manipulating it. In Python, all Python, that assignment statement doesn't create 2 objects. There's a single object. That object has 2 names. One name is A, the other name is M. And so as it's manipulating the object, it destroys the original matrix. So when we're doing our own work, it's in our best interest to actually create copies of the matrix and operate on the copies. We have a matrix called x transpose x. Our solver program solves AX equals B. So we want to go ahead and take our x transpose x matrix, put it into a name called C matrix for lack of better name. We want to take our x transpose y vector, put it into a name called D vector, and then we're going to go ahead and send them to the linear solver and recover D vector back. Oh, it looks like, so what we have at this point, this is D vector before we enter the script. This is D vector when we come back from it. So all these are simply name changes to preserve the original matrix.
Thank you very much. This is super helpful. It's like the first time I've been seeing matrices, so this is kind of overwhelming.
You'll get that in your calculus class then.
All right, cool. Thanks.
And let me turn somebody off who is talking in the background. I'm going to mute everybody if it'll let me. Oh, it won't. Farang, mute everybody, please.
I will.
Okay, I just unmuted myself. If you have a question, unmute yourself and ask it. That's not a problem. I'm going to mute myself again.
I have one question. Can you explain correlation and covalence? Covariance, I mean. Can y'all hear me?
I hear you.
Okay.
Is it a question for me or for Dr. Cleveland?
It doesn't matter. I just want to understand both of them.
So go ahead and ask the question again.
Can you explain what correlation and covariance is? Because I was re-looking over the video from last class, and you made a chart of, I think, covariance, and then you said that the numbers don't matter until we look at the correlation. So I was confused about that.
I will cover that again today, but just because you've asked, covariance gives us an idea about the direction of the relationship, whether it is positive or negative. When it's positive, you know that you have a direct relationship. When variable A goes up, variable B goes up. When variable A goes down, variable B goes down. When it's negative, you're having an indirect relationship or a reverse relationship. So when one of them goes up, the other one goes down. But the number itself cannot be very informative. So we used a normalized version of covariance, which is the correlation coefficient. And one of the methods to calculate correlation coefficient is the Pearson's R. And it's a value between -1 and 1. When it is close to 0, we have very small or no relationship. When it's close to 1, we have a strong and positive relationship. When it's close to -1, we have a strong and negative relationship.
So basically what you're saying is that the covariance tells us whether it's a direct or inverse relationship and whether it's positive, and then correlation gives us the strength of the relationship. Okay, thank you.
Or you could look at the picture that I just drew. You have blue dots and red dots. So both correlation and covariance communicate similar information. In that picture, under the word correlation, you see all the blue dots?
Yes.
Does knowledge of any blue dot where you are in X give you very much information about Y?
No.
It does not. Same question, red dots.
Yes.
Yeah, the red dots, if your X is over here, your anticipated Y is down here somewhere. If we get up into the big values of X, we expect Y's up here. That is telling us that X and Y are correlated. The covariance is telling us the magnitude of that, because our range of X values is like that, and our range of Y values, well, actually I drew this badly because I want to make the picture look good. Covariance gives us the information for whatever the variability of X is, what's the equivalent variability of Y. So if we have a lot of variability of X and no variability of Y, which is what we would have in this first blue dots, the covariance is quite poor. X is hugely variable, Y is not. And the two interrelate to one another, and they help us understand as well as construct data models. And I don't have a good visual thing of covariance. I mean, I can draw it with dots, but I would need to introduce a third axis to really make it meaningful. And I'm not going to attempt that. You'll see today in lab, at some point, Farang is likely to show you a covariance matrix, and you'll explore the off-diagonal terms in words just like this, just a discussion just like that on their significance. If actually, maybe I can pull this. I'll see if I can confuse the crap out of you all in the next minute. We'll stay with the same picture. So we still have our X and Y axis. And let's say that is our data. It's really quite easy to look at what our correlation matrix is going to be. Covariance matrix. this is going to be beta 0, beta 1. Perfect fit. Let's say that's our situation. We have all those things that line up just like that. Our off-axis terms are 0, and our diagonal terms are very close to 1, or our coefficients, depending on how we represent it. So this tells us that we have an extremely, almost perfectly strong correlation between x and y. When these zeros, the off-diagonal terms, become non-zero, it's telling us that our picture is starting to look like that. And if they're really non-zero, we could get really terrible things. Well, not terrible in a value sense. Terrible is in a useless sense. So that is the information conveyed by covariance and correlation. And then the computation of the off-diagonal terms, the reason it's called covariance is because it involves both x and y values when we calculate a variance. So we pool things and then calculate variances or standard deviations, if you will, on pooled things, and that's what goes in the off-diagonal term. All right, that should have you all thoroughly confused. I will get off the phone now.
Okay, we can begin our lab session. Are you ready for a short and quick review?
Yes.
Awesome. So we are going to talk about linear regression again. What is linear regression?
Linear regression is a line we use to create a line of best fit.
Awesome. I actually like your definition way better than the general definition of it. Generally, we say it is a basic predictive analytics technique that uses historical data to predict an alpha variable. But you are completely correct. It is a linear model that we use to fit our data and then use that to either explore the relationship between two variables or more variables, and or to predict something that we do not have. Okay. How does linear regression work?
It works by taking two columns or two sets, and then we compare them, and then we visually or statistically create a best line of fit, do them to predict future values or values within the data itself.
Okay, so I have two sets of numbers, let's say time and speed. And if I compare them and plot them, that is linear regression.
Or
there is a rather important step that you are missing.
Can you say it again?
So I have two sets of numbers, time, speed, for example. If I just compare them and plot them, that is not linear regression.
Do you have to normalize them or something?
we need to fit a model to it.
Yes, and that model is the linear regression. So when we say it is a linear model and it's a line, what does that mean?
That our model is a straight line.
That means that the equation for that model will be that of a line with two parameters. What are those parameters?
Beta and alpha.
Which stand for?
Slope and y-intercept.
Slope and intercept, exactly. So when we try to fit a linear regression model, what are we trying to do? Will any alpha or beta work for us?
No, that's what you're trying to find. You're trying to find your slope and your intercept. You're trying to find like something based on the 2 points or based on your data.
Okay, and what would I call my best beta and alpha? So let's say I think beta equal to 2 and alpha equal to 5 is the best. Hayden comes out and say, no, beta equal to 1 and alpha equal to 10 is the best. How can you tell which set is the best?
You use the formula.
What formula?
The beta and alpha formula that we got last class.
I'll take that. So previously, in the previous weeks, we used to play around with values of beta and alpha or slope and intercept and visually see which fit was better. Last week, we talked about a method known as ordinary least squares, or OLS, that would help us find the best values for beta and alpha, and that had formulas that we used. But that is not the only way. OLS is not the only way to estimate beta and alpha. So let's put a pin on that. Let's keep it there. Now, I want to take you back to the lectures and lab sessions where we talked about probabilities. Do you remember this equation?
I remember seeing it.
Okay, that's good. Anyone else?
I've seen it from my previous stats class.
Okay, do I have anyone who may want to tell us what this is and what it does?
Does it plot the range? Is this for interval?
Okay, let's go part by part. On the left-hand side, what do you see? This little cute P, what does it stand for?
Probability.
Probability. Okay, very good. Probability of X belonging to, when you see mu and sigma next to each other, what comes to your mind?
Population.
What about population? Yes, distribution. Okay, so we are calculating the probability of a sample X belonging to a certain population. When we know the mu and sigma, the mean and the standard deviation of that population. That's what this weird looking equation does for us. That's it. There is nothing scary about it. So let's say that we want to know the probability that a sample equal 3 comes from a distribution with a mu equal to 3 and a sigma equal to 1. And we also want to know the probability that the same sample comes from a distribution with mu equals 7 and sigma equal 2. And then we want to know which one is more probable. So basically, if we calculate the first part and we calculate the second part, we can compare them and answer the third question. So, do I have a volunteer who wants to help me explore these 3 tiny code cells?
Ooh, can I do the first one?
Okay. It's kind of a package like you go to Costco. You have to pick the 3 of them together.
Oh, no, that's okay. I actually don't have a Costco membership, so I'll just...
Okay.
So the first one, we are importing NumPy under the alias NP, and then Pandas under the alias PD. We're importing statistics and scipy.stats. And from matplotlib, we are importing pyplot under the alias PLT.
Amazing. Then
now we're going to use from scipy stats.norm.pdf for the numbers 3, 3, and 1, which will result 0.3989422 804014327.
Okay,
Next,
so
the same thing.
wait a moment. That stats norm PDF function that you called from SciPy,
Yeah,
what is it doing for you?
It's giving us the number you see in the output.
So it basically is
Doesn't it
doing
stand
this.
for? Oh yeah.
It is doing this calculation for you. Okay, so if you want to do this calculation, what numbers do you need?
X, mu, sigma.
Okay, don't you need your pi?
No.
It
Do
was
you?
a peanut butter pie. You better have not rejected. It's okay. So, yes, you are right. We need 3 parameters. That's why you have 3 arguments here. 3, 3, and 1. Where are you getting these numbers?
Well, the
From the
sample.
problem.
The sample is 3, mu is 3, and sigma is 1. You can read it above.
Okay, so that is the order. Sample, mu, sigma. What is the number that you get? You just read the 2 or 3 first digits, please.
0.398.
Okay, and what does that tell you?
That's our probability density function form number.
That was a politician's answer, which is correct, but doesn't mean anything. Give me what does it tell you? What can you understand from that number?
Can I lend a hand?
Yeah.
So the number we got gives us the probability of X being in that population distribution.
Okay, so what do you know right now?
So what do you mean?
So you calculated that and it came out to be 0.4, let's say.
Yeah.
Can you give me one sentence based on this calculation?
Okay. Based on this calculation, the chances of our sample being part of the distribution is very slim. And not
That
likely.
was a subjective judgment on a 40% chance. So
Wait.
here's the deal. If I tell you that if you walk across campus from 8 to 10 a.m., there is a 40% chance that you are going to win $1 million. Will you do that?
Yes.
So that's not that small of a chance, is it?
No.
Okay. So as much as you can, try to avoid passing judgments on the numbers and try to report them as they are. So you were doing very well. Let's start again. Based on what we've done, there is a 40% chance that a sample of 3, go on,
comes from the distribution of mean of 3 and standard deviation of 1.
Thank you very much. It is quite ironic that at the beginning of the semester, you all knew how to speak English and we had to teach you how to speak Python. And now you know how to speak Python, but I have to help you put it in English. Quite interesting. So what happens next, Caden?
You mean the next code cell?
Yeah.
You're just running the exact same function, but this time with a sample of 3, a mu of 7, and a standard deviation of 2. And this time we're getting a much smaller probability.
Which means?
It's unlikely that we have an average of 7 when, or it means it's unlikely to me that the population is in fact that.
So if you had to choose between the two.
First is more probable.
Exactly. Okay, thank you very much. So it is much more likely it came from the first distribution. The PDF equation has shown us how likely those values are to appear in the distribution with certain parameters. Keep that in mind for later, but what if we had a bunch of points we wanted to estimate? So let's say that instead of 3, I wanted to know the probability that 3, 5, and 7 belong to a distribution with mu equal 3 and sigma equal 1.
Then you would just run the same thing, but change the x each time.
Okay, so let's say I calculate that for 3 and for 5 and for 7. How do you want to report that?
You would report you would say in this order, the sample's probability of being in the distribution is from most likely to least likely.
So let me clear the question a little further. You are not dealing with a single sample anymore. You're dealing with a sample of 3, 5, and 7.
Oh, wait. Would we add the probabilities together?
So that's one way to answer the question. I have summation as one answer. Do I have any other answers?
I think we should multiply.
Multiplication comes the second answer. So cast your votes in the chat box.
Can you repeat the question?
So let's say that I have a sample set. I have 3 values in this set, 3, 5, and 7. The question is, what is the probability that this sample set comes from a distribution of with a mean of 3 and a standard deviation of 1? Are you going to calculate the probability of each one of them and add them? Or are you going to calculate the probability of each one of them and multiply them? Or are you going to do something else? Currently, I had these 2 answers.
You're going to multiply them.
So Wally jumped ships. I have multiplication all over the place. Brandon the Brave, are you going with the rest of them? Yeah, okay, so I have no other answers. All of you say multiplication.
We're typing our answers.
Okay, all I see in the chat box is multiplication. Question: why? And do not say because the others said so.
Well, there goes my answer. But I would say because it's all in one data set. So I assume because it's not with replacement or anything like that, that since it's all from one data set, you would have to multiply. It was, let's say, multiple data sets, multiple sample sets, then you would add them together. If that makes sense.
Okay, that's one way of thinking about it. Do I have any other answers to the why question?
Gut feeling.
I think I would say that we would multiply because they're independent of one another. So they don't rely on each other.
You're getting close. So for a moment, forget what we've talked about right now. Go back to maybe a month ago, 3-4 weeks ago. If you have anything in your memories about it. Under what circumstances we added the probability of 2 events?
We would
think about the card games and everything. Come again?
We would do that when we have several outcomes that we're interested in a success outcome. So
you would.
So
can you give me an example?
If I was interested in drawing a 2 or a 5 from a deck, I would add the probabilities of drawing a 2 plus the probability of adding a 5.
Okay. So that or that you said played an important role.
Yeah.
Okay. Under what circumstance you would multiply them?
consecutive probabilities. So if I want to draw a 2 and then a 5.
Okay, and this is how I'm going to tie this to Abby's comment. When your events are dependent, it's a different story than when they are independent. So we're going to assume that our bunch of samples are coming from some normal distribution with mu and sigma as mean and standard deviation, and they are all mutually independent from each other. In this case, the total probability of observing all of them is the product of obtaining each data point individually. So based on these two assumptions, we are going to say we calculate the probability of the first sample coming from that distribution, multiplied by the probability of the second sample coming from that distribution, multiplied by the probability of the third sample coming from that distribution. So, example 2. What is the probability of 2 and 6 being drawn from a distribution with mu equal 4 and sigma equal 1? I calculate the first one, I multiply it into the second one, and that's what I get. That is quite a low probability. So, if I have 1,000 samples in my sample set, what will happen? If I have a sample set with 1,000 samples in it, and I want to calculate the probability of this set coming from a distribution, what would I do?
So you have a sample set that has 1,000 numbers in it. You're trying to determine whether the sample set came from a distribution?
Yes. In this example, I had 2 samples in my sample set. In my current question, I have 1,000 samples in my sample set. What should I do?
I guess you would do the same thing and multiply.
Exactly. Exactly. I would do exactly the same thing. In that case, it would be the multiplication of 1,000 values. If I have 1,000,000 samples, that will be the multiplication of 1,000,000 values. Okay? So, the other method, other than OLS or ordinary least squares, is the maximum likelihood estimation, or the maximum likelihood method. So, at this point, are you ready to be bored to death by mathematics?
Not me.
Not you, yes, I know. So, MLE is used to specify a distribution of unknown parameters. Then using your data to pull out the actual parameter values to go back to the pin that I gave you earlier. So, in maximum likelihood estimation, we actually do some kind of a reverse engineering. We assume a distribution and we do some analysis to find the parameters of that distribution. Okay? The noise, let's have a look at these two. Is this equation y equals to theta 1x plus theta 0 up until this point familiar? Does it ring any bells?
Looks like the equation of a line.
Exactly. That is the equation similar to
y equals mx plus b.
Yes, or this one. So we use m and b, we use alpha and beta, we use theta 0 and theta 1. As long as you know that this one is the slope and this one is the intercept, you are good as gold. Not gold, maybe copper, but anyway. So what is this little weird thing doing here?
Is that for like the margin of error, or
you got very close to it. That stands for error. Yes. Because no matter what we do, there will always be some error, right?
Yeah.
So.
Because it's still an estimation, right?
So when you were looking at plots like this one, do you remember this? Please say that you do remember this from last session.
Potentially, yes.
Okay.
Yes.
Okay, good, good. So on a plot like this, where is my error?
What do you mean by where's your error? Like, where's your variability or what?
No, I mean, if you wanted to show me the error of prediction or the error of modeling on this plot, what would you point at?
You would take the distance from your best fit line to your data points.
Exactly. So for every single point, the difference between the red line until that point will be the error of estimation. Okay? Deal?
Yeah.
Okay. So if I tell you that all these errors, either positive or negative, falls quite symmetrically around my red line, would you agree with me?
Except for that very first part, yes.
So in the majority of cases, you have some errors that go up, some errors that go down, and they are quite symmetrical, right? So, no, yes, maybe?
Yes.
Yeah.
Okay. So, we have agreed on symmetrical, and we have agreed that they are around the red line, the linear regression model. When I'm at the linear regression model, let's say a point like this one, what is my error?
Your error is the distance between the dots.
Is there a distance?
In that same, what?
For this point that I'm showing, do you see a distance from the red line?
It's probably like a really small error, mostly approaching 0.
Okay, so let's assume that my error at this point is 0. And the further I deviate, the further I go from the red line, my error is going to get bigger. Now, listen to this. If I tell you that my error comes from a normal distribution with a center of 0 and some standard deviation, can you agree with that?
Can you say again?
My error, all of my errors, comes from a normal distribution centered at 0 with some standard deviation, some to the right, some to the left.
Yes.
I have one person who agrees with me.
So what we're saying is that the line is the normal distribution and the difference from the line is the standard deviation, right?
No. What I'm telling you, if you want to do some kind of parallel work between the normal distribution of errors and this plot, the mean of that normal distribution is going to fall on the location of the red line. And then as you go up or down in the plot, you will go right and left on the normal distribution. If we have a bunch of values that are centered around 0 and they are symmetrical, aren't we dealing with a normal distribution?
Yeah.
I have another one who agrees with me. Anyone else? Do I have anyone who disagrees with me? I feel like one of those, I'm not sure if you've ever seen one because you've probably been here during COVID, but when it wasn't the COVID era, you would just walk to the campus library, and it was very common to see some kind of preacher standing on top of a chair and giving lectures to people and calling them to all kinds of different religions. And many people were just there for the fun of it. They didn't really care about his preaching. They didn't agree or disagree with him. So don't be like that with me. You either agree or disagree. If you do agree, that's fine. If you don't, tell me why.
Okay, so in this normal distribution, are we taking into account all the errors, or what are we taking into account?
All the errors. So let's say that I start from this point. Let's say this error is -3. Then this is probably -2. Then this is -1. I get all of these, and then the error here is probably +3. So
okay, we just went over this in my stats class. We can't have a normal distribution because we can't have negative values.
If your normal distribution is centered at 0, why can't you have negative distributions? Let's have a look at this. Do you have 0 values here or not?
Potentially.
So half of the values under this distribution is positive. Half of it is negative. And it is centered around 0, isn't it? So in fact, I'm going to ask my question again. Do you think that my errors can potentially follow a normal distribution like this, with a mean of 0 and some standard deviation? Cast your votes in the chat box.
Would a better way to explain this be the line is the, let's say, the mean or whatever, and then the dots are then a certain standard deviation away from the line itself. You know what I'm saying?
If you think about the relative location of those points with respect to the red line, let me go back to it. So the relative location of these points with respect to the red line, then yes, we are saying that these points are falling around that central line.
Mm-hmm.
Okay. I haven't seen any votes and I haven't seen any arguments, so I'm not gonna spend more time on this. Let us move on. We are going to assume that our errors come from a normal distribution with a mean of 0 and some standard deviation. Here it says the noise parameter error is basically why the points or samples do not fall exactly on the line. And then it goes over the assumption that I just talked to you about. So this model has 3 parameters. What 3 parameters do you see?
X1.
Where is X1?
Is that degree?
Are you looking at the same screen as I am?
Oh.
So look at this model and tell me how many parameters you see here. Y and X are your variables. What parameters?
Theta sub 1.
Mm-hmm.
Theta sub 0 and
error. You can say error, but since we are modeling error as this, we basically have this sigma. So 3 parameters, theta1, theta0, and sigma. Thank you. Our main goal is to find the best parameters for the slope and intercept of our line. So the goal has not changed from last session. We are still trying to find the best possible values for slope and intercept. We are just following a different path towards it. So let's rewrite our model from above as a single conditional distribution. So I'm going to put these together, and I'm going to say that my y basically comes from a normal distribution of this and this. Mean, standard deviation. This is equivalent to pushing our x through the equation of the line and then adding noise from the zero mean normal distribution. Now, we can write the conditional distribution of y given x in terms of this equation. Conditional distribution of y given x. Where did you see that last time? Where did you see an equation like this last time?
About 30 minutes ago.
Exactly. So this is the same equation. So we are going to merge this and that and get something like this. So basically, for each point, we are going to calculate the probability of that sample belonging to that distribution. Each point is independent, that's an assumption, and identically distributed. So we can write this likelihood function with respect to all of our observed points. What did we say about a case where we have multiple samples?
Multiply, I think.
Exactly. What does this stand for?
Multiplication.
This is exactly like sigma, but instead of summing up, we are multiplying. So for cases where I have a bunch of samples, I'm going to go with this equation. Now, do you remember when I told you what I should do if instead of 2 samples, I have 1,000 samples? What was the answer?
You still multiply.
What if I have 1,000,000 samples?
You still multiply.
What is one challenge that can happen when we are multiplying millions of numbers?
We could potentially mess up somewhere.
That is correct, but that is correct about every single act of human beings. But what is specifically concerning about multiplication of many, many numbers?
We overload the computer.
Because?
It's too big.
Because it can get too big, correct. So the next step is to find the parameters which maximize this function. But to make our equation simpler, let's take the log of our likelihood. So we are going to take the log of this equation. Recall that maximizing the log likelihood is the same as maximizing the likelihood since the log is monotonic. So when you find the parameters that maximize your log likelihood function, they will basically maximize your likelihood function as well. The natural log cancels out the exponential and turns products into sum. So now, instead of multiplying that thousands and thousands of numbers, you are summing them up. That kind of keeps the scale lower and smaller. So I take the log, I clear these, and at the end, I arrive at basically this. So to clean things up a bit more, let's write the output of our line as a single value. This is what we had last session, equation of a linear regression. Y hat equals to theta1 slope multiplied by x plus theta 0 intercept. Now, our log likelihood can be written as this. How many parts do you see on the right-hand side?
A lot.
Wait,
like what are my parts?
If I say I see 2 parts, is that something that you can all agree with?
Yeah.
Okay. Do you see any variables in the second part?
Y.
Y, okay, cool. Do you see any variables in the first part?
No.
No. So basically, there is nothing about this part that we can maximize or minimize. Okay? So what we care about is this second part. Something else that I personally do not really understand the reason for it, but apparently people do not like to work with negative signs. So instead of maximizing this, we are going to minimize the negative of this. Does that make sense?
Yes.
So instead of maximizing A, we are going to minimize minus A. And that will give us this. To minimize the negative log likelihood with respect to the linear parameter or the thetas, we can imagine that our variance term is a fixed constant, which we did, and we said we only care about the second part. We can throw out any constant terms and elegantly write what we are trying to minimize. This, which is basically the second part, is what we are trying to minimize. What is y?
The original y from the sample.
The true value of y. What is y hat?
The linear regression y.
The estimated, correct?
Yeah.
So when I say that I want to minimize y minus estimation of y to the power of 2, what am I doing?
Are you finding the error here?
Kinda, and I'm trying to minimize the error. Correct? So yeah. I'm basically saying that I want a slope and intercept that would give me the minimum error possible. Does this sound familiar? Wasn't this the exact same goal of OLS? Ordinary least squares?
Yeah.
Yeah.
In both cases, our goal is the same. We are trying to reduce the errors, but our approach to it is different. So the maximum likelihood estimate for a linear model is the line which minimizes the sum of squared errors. Now, let's solve for parameters. We have concluded that the maximum likelihood estimates for our slope and intercept can be found by minimizing the sum of squared errors. Let's expand out our minimization objective and use it as our index over n data points. So let's say I have n points, n samples in my sample set. I'm trying to minimize the difference between true value of y and the estimated value of y. I'm trying to minimize the distance. The square in the SSE, sorry, I jumped over it. Instead of y hat, I'm putting the equation of my linear regression. That makes sense, right? Because my estimation comes from my linear model. My linear model works with the slope and intercept, theta 1 and theta 0. So basically, this is what I'm trying to minimize. The minimum can be found by taking a derivative with respect to each of the parameters, setting it equal to 0, and solving for the parameters in turn. I'm not going to get into that. Setting the derivatives equal to 0 and solving for the intercept will give us this equation for theta 0. and this equation for theta 1. So similar to OLS that gave us two formulas, maximum likelihood estimation also gives us the two formulas. Calculate theta 1, you calculate theta 0 based on that. I know that this has been a little more math than we usually do, so I'm going to pause and ask if you have any questions about what has happened so far.
I don't have any like specific questions. It's just a lot. But so why would we want to use this one versus the other one that we learned? Like, what are the...
That is a very good question, but I don't want to, let me see if I actually asked that. No, I didn't. That was one of my candidate questions for your exercise at the end of the lab.
Just like simple application, I think that'll help me understand a little bit better.
Depending on the nature of your data, sometimes one of them helps you better. Let me give you an example. For example, when you are dealing with highly imbalanced data, or with data with extreme outliers, one of these methods might be a better choice to go with. But to give you a solid answer, OLS versus MLE. This might be a good reference. I'm putting it in the chat box. Also, let's see from my better references. Oh, here you go.
While he's looking, OLS always refers to the parameters have to be linear combinations of each other. Maximum likelihood estimate does not have that requirement.
Okay, thank you.
If that is not a question for me, can you please mute your microphone?
Mute us all.
Sorry. So, do I have any questions on how we did maximum likelihood estimations? How did we end up with the formula for theta 1 and theta 0? No? Abby, if you're talking to me, I can't hear you.
Oh, no, I was just looking at the partial derivative.
Mm-hmm. Okay.
I was just kind of curious because like I remember doing this and calculus was like kind of cool seeing all this stuff again.
I'm not sure if you thinking this is cool is a good thing or a bad thing, but
it's a good thing. Oh my God.
Thanks for being interested in it. So, let's put all this in Python. So we are going to define a function. We're going to name it find_line, and it is going to ask for xs and ys. What is xs and ys? Come on.
Is that the x and y?
They are basically, yes, are variables. The input variable x, thank you, Aaron, and the output variable y. So first, I'm going to calculate the length of xs. What is this when we are speaking English?
The
sample size. Yes, thank you. So then I'm going to calculate x bar and y bar. What are these when we are speaking English?
What is that sum?
I'm adding all my x's and I'm dividing them by sample size.
Is that the axes?
Is that what?
The axis? Okay,
What do you
we
mean the
count,
axis?
like what we count the x by, what we count the y by.
When I add all the cases of something and I divide it by their total number, what will I get? You have 15 weekly exercises in this course. If I add your grades in all of them and I divide them by 15, what will I get? I have 2 answers in the chat box. Thank you. That is the average. So here I'm calculating the average of x and average of y, or mean of x, mean of y. Okay, now I'm going to calculate a slope. How? With this equation. For I in a range of n, by this beginning of my for loop, what am I going through?
You're doing it for every single samples size?
Thank you very much. Yes, so I'm going into my sample, and for every single sample I have in my set, I am calculating this. The value of x minus the average of all x's multiplied by the value of y minus the average of all y's, and I'm going to divide that by the value of x minus the average of all x's to the power of 2. This is exactly the same equation. So what you see here is the implementation of this equation in Python. Okay? Then when I calculate my slope, I'm going to calculate my intercept. How? By using this equation. So when I have my theta 1 or slope, my intercept is going to be my y bar minus slope multiplied by x bar. And that's how I'm calculating my intercept. And this find line function that we are defining is going to return the slope and intercept to us. Okay? Any questions?
No.
Okay, cool. Now, let's work on a hopefully familiar problem from exam 2, which we also worked on Thursday. We had a table of recorded times and speeds from some experimental observations. We are going to use MLE this time to find the intercept and the slope. So this is the table that we have. I'm going to create a list of time values, basically 0 to 10, and a list of my speed values based on this table. I'm going to apply the find underline line function on time and speed. Question: what does find underline line function do for me?
It calculates the slope and intercept.
How? You know the answer. This is not a trick question. Using the formulas. And when you say the formulas, what formulas you're talking about?
Equation of a line.
And
finding the sigma.
the formulas that we find today, where did we get them? How did we come up with those formulas for theta 1 and theta 0?
Was it from the PDF or no? No, they make
Yes,
the
yes.
make
The method that we used the equation of PDF. So on Thursday, on last session, what formulas did we use to calculate intercept and slope? What was the name of that method?
I remember, but I just
at this point, feel no shame in going back and opening that notebook.
Can we get a hint? I remember.
There you go with your hint. Dr. Cleveland is giving you the hint.
Oh.
Guys, read. It's English.
OLS.
OLS was the method that we used on Thursday. OLS gave us two equations to calculate a slope and intercept. What was the method that we used today?
MLE.
Yes, which stands for?
Now you got it. Yeah.
Maximum likelihood estimation.
Yes. What was the name of Russell Crowe's character in The Gladiator?
Ah. See, it's on the tip of my tongue. I don't remember. Wasn't it Gladiator?
No, it started with Maximus.
Maximilius. Maximus, yeah.
Maximus Decimus Meridius. So if it was Maximus Lessimus Iridius, that would be MLE. Anyways, so we used MLE to come up with two equations for slope and intercept today. Then we used those two equations to define a function, and we named that function find underlying line, and we are using it here. Deal?
Mm-hmm.
Okay. Now, here's a trick question. What package am I getting the find line function from?
Can I say it again?
What package am I getting the find underlying line function from?
Was it statistics?
What is Dr. Cleveland telling you?
Oh, sorry. Let me check.
We make it?
We made it. It was a custom made function or user defined function. This is where we defined it.
I see.
So
Yeah,
my question,
yeah,
is
sure.
there a standard issue version of that, or is it just we make it ourselves?
Of course there is.
Oh.
Of course there is. So we ran it and we got these two numbers. How many of you have access to your previous lab's notebook?
Me.
Go to it and see if these two numbers are the same that we got from OLS.
It was in the lab, right?
Mm-hmm.
They are the same values.
The same values. Exactly the same value.
Yeah.
Awesome. Okay. Now we are going to use these two values to create our linear model and then fit it to our data. So alpha is going to be our intercept, beta is going to be our slope, y-pred is going to be our estimations, and we are going to get this plot. Harper Hill, come out and defend this fit.
This is a pretty good fit because it's not very far off at any point.
Okay, on which ranges would you trust it more, and on which ranges would you trust it less?
From around 2 to 9, I'd say it's pretty good. In the middle of that, it's a little shaky, and then getting towards the end, like 0 to 2 and past 9, that's getting further off.
Okay, and what would you say about the relationship between time and speed based on this plot?
They have a positive relationship.
Okay, why would you say that? Why would you say that?
As time increases, speed increases.
Thank you very much. Awesome. Thank you, Harper. So, do you all agree with Harper's description of the plot?
Pretty much he hit
Yes.
everything, so yes.
Okay. So let's say that you want to, I don't know, make some investments, and you go to Harper's brand new luxury investment consulting company. The big man himself agrees to talk to you. So you walk in, the room is dim, sharp lights are coming from the background. He's like a very young Jack Nicholson sitting in the room behind his desk. You sit, you ask him about his predictions and his understanding about how much money you will get if you invest a certain amount. He looks at his linear regression model, something like this, and he says, my model is doing good for this range and not very good for that range, and then it gets a little off in this area. Would you feel comfortable making the investment if he talks like that, or if he comes out and tell you, my model is off by this amount in this range, and my overall error is this much, and I'm this confident in this model?
The second way.
The second way. Do I have any other answers?
Depends on the rager he throws, but I think the second answer would be better.
Mm-hmm. Do I have anyone who wants to go with the first one? Okay. First of all, Harper, know your friends. Second of all, part of the deal is giving an accurate number or giving a numerical output is usually a better way of representing a model. But the big part of it is that when you throw numbers at people, they think that you know more. In fact, at least from personal experience, I believe that Harper's way of describing a model's performance is as important as coming up with a numeric description of it. But that's how the world is. So we need metrics that can help us assess the goodness of fit. Numbers that can describe how good a model fits a bunch of points or data. Okay, that's why we're going to talk about goodness of fit metrics. So far, we have assessed the quality of fits visually, Harper's way. We can make numerical assessments as well via goodness of fit or GOF measures. Let's discuss 3 of the most common metrics for evaluating predictions on regression machine learning problems. The first one is mean absolute error. Judging only based on the title, what do you think we are measuring with this metric?
Wait, can you say again?
Judging only based on the title. Do not read what I have written down there. What do you think we are measuring? Abby was laughing like we never read what you write. What are we measuring with mean absolute error, MAE?
We are looking at the error, and we're taking the mean of it as well, I suppose.
Okay. What happened to the absolute? Did you drink it?
Does it mean that we're taking the mean of every single error we got due from the line, and then gain the
Okay. So on the plot, on this plot, what is the error at this point?
Let's say like oh, do you mean in terms of standard deviation or in terms of the actual?
Only tell me the error. What is this distance?
Let's say like 18.
18. Okay. What about here?
Like 5.
What about here?
Like 1, maybe.
What about here?
2 or 3.
No. This
What's
is
negative?
negative.
Oh, negative.
Yes.
Okay.
Negative 2 or 3. What about here?
Also 2 or 3.
Negative 2 or 3.
Negative 2 or 3.
So whenever you're below the line, you're negative. Whenever you're above the line, you're positive. The mean absolute error is going to assume that regardless of being above or below that line, that is an error. So I don't care if it's -2 or if it's +2. I'm going to take the absolute values of all errors and get the average of that. Does that make sense?
Mm-hmm.
Okay. So I can't really read what Dr. Cleveland is saying, but I'm sure that he is parallel teaching. Thank you very much. So MAE, take the absolute of these and then find the mean. That is beautiful illustration. Thank you. So the mean absolute error, or MAE, is the average of the absolute differences between predictions and actual values. It gives an idea of how wrong the predictions were. The measure gives an idea of the magnitude of the error, but no idea of the direction. So because it deals with the absolute values, you have no idea of whether you are under predicting or you are over predicting. It only gives you an idea of how big or small your errors were. Does that make sense?
Yes.
Okay. It is thus an arithmetic average of the absolute errors, where yi is the prediction, xi is the true values, and so on. So to manually calculate MAE, that's what we do. We get the distance, the difference between true values and estimated values. We get the absolute value of that, and then we get the mean of that. That will be the mean absolute error. We can also use the mean underline absolute underline error function, quite descriptive, from the metrics package that is in Skylar, and directly calculate MAE. Either way, the number is going to be identical. Do you have any questions about MAE and how we calculated it? No? All good? Clear as honey?
Water.
Okay. So, 2 more metrics. Mean squared error and root mean squared error. So let's focus on the first one. Judging based on the title, what do you think mean squared error calculates?
The error, but the mean of the error, but we're also going to square it. So I
Change the
guess
order.
we're going to square the error and then
Mhm.
find the mean of it.
Exactly. So we get all those distances, we take them to the power of 2, and then we calculate the average. That will be mean squared error. Now, that was MSE. What is RMSE?
What is my root?
Second root.
I guess we add these squared errors together. We find the mean, then we find the square root of it.
Exactly. Exactly. So RMSE is the second root of MSE. As easy as that. So let's see what Dr. Cleveland is saying. Yes, take a square root of MSE and you will have RMSE. And the question is why? It's because of this highlighted word. So before I go into its description, what do you think will be the biggest difference between root mean squared error and mean squared error? Which one do you think?
Root mean squared would be smaller.
Okay, yes, RMSE is going to be smaller. What can you tell me about the units?
Oh, the units will be, I guess the mean squared unit would be like to the second power.
So if I'm looking at samples of length and I'm working with inches, what will be the unit of MSE?
Inches squared.
Inches squared. What about RMSE?
Inches.
Okay. So if you are measuring something in inches, let's say the screen size of your TV, would you prefer to deal with an error metric that has the same unit or that has the same unit to the power of 2?
The same unit.
Why?
It's easier to translate.
Exactly.
It's easier to compare.
Yeah. Okay, awesome. So the mean squared error, or MSE, is much like the mean absolute error in that it provides a gross idea of the magnitude of the error. It measures the average of the squares of the errors, that is, the average squared difference between the estimated values and the actual value. The MSE is a measure of the quality of an estimator. It is always non-negative, and values closer to 0 are better. So similar to mean absolute error, MAE, we want it to be closer to 0. An ideal case would have an error of 0. Okay. An MSE of 0, meaning that the estimator predicts observation of the parameter with perfect accuracy, is ideal, but typically not possible, of course. Taking the square root of the mean squared error converts the units back to the original units of the output variable and can be meaningful for description and presentation. This is called the root mean squared error. RMSE is the most widely used metric for regression tasks. Here's the formula. And again, we are calculating it by hand and by using the metrics package. And you see that we are getting identical numbers. So for the same case and same variables, MSE is 108, RMSE is 10.4. Do not think that MSE is useless. Just because RMSE gives us a better interpretation because of the units thing doesn't mean that MSE is useless. So that's another metric for itself. So let's see what Dr. Cleveland is writing for us. Correct, to keep at proper scale. I can't read that. UKE when MSE? That is not UKE, is it?
It's when MSE is less than 1.
Oh, yes. Okay. Yeah. Okay. So let's see what else we have. The last metric that I've put here for you is R2 or R squared. Amazingly popular with people involved with the statistics. I still don't know why they love it so much. It's probably that it's kind of easy. And that's what non-engineers do. They go for easy. So the R2 or R squared metric provides an indication of the goodness of fit of a set of predictions to the actual values. In a statistical literature, this measure is called the coefficient of determination. Why? Because they like to pretend that they're different. Just kidding. This is a value between 0 and 1 for no fit and perfect fit. So if it's 0, it's no fit. Unlike the others that you wanted to have lower numbers, with R2 or R squared, if you have a low number, that's bad news. That means that your fit is not good. If it's close to 1, it's close to perfection. It provides a measure of how well observed outcomes are replicated by the model based on the proportion of total variation of outcomes explained by the model. So it is looking at a different thing. So it calculates the residuals and it calculates the totals, and then 1 minus residuals over totals gives you the R squared. Again, extremely useful metric, but I warn you to not get too attached to 1 or 2 metrics out there. So we talked about 3 goodness of fit metrics for regression type models. What percentage of GOF measures you think we've covered so far?
Can you say it again?
We have talked about 3 metrics, correct? 3 or 4 metrics. What percentage, what share of all the goodness of fit measures out there you think we've covered so far?
Like what's
less than 10%?
Even smaller.
1%?
2%.
There's no specific count for it. Even if you go out there and look at the literature, every month, every week, people are coming up with new metrics because you
They want to be different.
Yeah, they will be different. Each goodness of fit measure describes a different aspect of your model's performance. And then depending on what you want to do with your model, what is the purpose of your modeling, you may need a different set of metrics. So 2 important takeaway messages that I will probably repeat more times until the end of the course is: be mindful of your goal of study and never rely on only 1 goodness of fit measure. You need to look at the performance of your model and the goodness of your fit from different aspects in order to achieve a more wholesome understanding. Deal?
Deal.
Okay.
But
Now,
I do actually have one question.
Awesome. Go on.
So how do we determine, like, because it seems like data science is almost an art as much as it is a science.
Yeah.
How do we determine, like, which you just said it and I cannot.
Goodness of fit measure?
Yeah, goodness of fit measure we would use.
So I will ask Dr. Cleveland to also answer this question, but I will give you my understanding of it. Depending on what level of work and what level of thinking you are doing, the answer to this question will be different. If you are doing simply the job of someone who is doing some operation, you go to a company, they tell you that we want these metrics, and you calculate them and you give it to them. But if you are the person that is the brain of the operation, there are two ways that I would recommend. First of all, literature. You go out there and you read what other people are looking at for the specific topic or problem that you're having. What are they saying? What are the limitations of the goodness of fit measures? What are the advantages of them? That's one thing. The other part, as I said, you have to sit down and think, what do you care about in that specific modeling effort? Let me give you an example. Part of my research is on predicting the flow state of intermittent streams. So these are rivers that go dry for periods of time in a year. They might be dry for 2 months, for 6 months, depending. In my modeling effort, I really cared about how well my model was capturing those zero flow events. So I actually went on and I calculated something as a zero flow accuracy. And I looked at that specific part of my model's performance. So that's what I would suggest. Literature, and think about the problem and what you're trying to do with your model. I will pass the mic to Dr. Cleveland and see what he has to answer.
Oh, I was turned on all the time. Good thing I wasn't muttering. Your goodness of fit selection is largely determined again by what you need to achieve. Let's go back to our earlier example. We don't need to do no screen. When we had the e-commerce database, none of those data entries in the database produced zero revenue. So we don't care that much about predictive accuracy outside of how to make more money, not how to make how much money. Another example might be celestial mechanics. We're flying a spacecraft from the Earth to Mars. A 0.001 degree error will miss Mars by 7 years. And we'll have a hard time making enough oxygen to get back to make it to the end of the movie or to make the second sequel to the movie Mission to Mars, or whatever we name it. So in that second case, your goodness of fit measures, you're probably going to try to do every imaginable one you can find because you want to guarantee to your astronauts that they're going to at least hit the planet you're aiming at. And that largely drives your goodness of fit decisions. The other confounding issue that we haven't really focused on at all, because the tools aren't readily accessible. They exist, but they're not easy to wrap our brains around, is when you have more than 2 variables. Now you're in 3-dimensional space as a minimum. You can't plot it. You get 5 or 6 variables. That's a 6-dimensional hypercube. You can't plot. There's no way you can visually render it. In those cases, then we are desperately dependent on multiple goodness of fit measures. In my work, I have created models in the past that depend on 5 and 6 variables, and I can plot versus 1 variable and get really phenomenal fits on what we're trying to predict, but the other 3 are crap. So ultimately, what we did in that case, and that's a common practice, is we plot our modeled output versus our observed output and compare that to an equal value line. Because if it was a perfect model, how should that fall out? We don't need a picture. A perfect model, the prediction and the observed should be the same. And for things that have multiple input variables, the only way you can, a way you can visually represent it is model versus observations, equal value line to guide the eye to what things look like. And those, you can produce a an error value that's relative to that equal value line and treat it as if it is actual data and produce goodness of fit measures for that. But that's where you are. It's an important task, and you're negligent if you don't try any goodness of fit. If it's something you can plot, you can always back up your decisions with a picture. That's about all I can say goodness of fit. I have a little verbal joke in my window here on political science, where's the science? And then you ask the question, data science, where's the science? Of those two, at least on the data science one, you can probably find an answer.
And just to add something to Dr. Cleveland's answer, something that we will discuss in a few weeks is detecting fraud in bank interactions, for example. How many interactions do you think happens for Wells Fargo users in a day in the country? Give me a number.
2 million.
What was that, Jordan?
2 million.
2 million. Okay.
14.
Out of those 2 million, how many you think are fraud?
75%.
What?
Whoa, 75.
I would say 75.
I don't trust that bank. It can't have a bad reputation.
I'd say 7 to 8%.
I would say 5%.
Well, how
It
about
is actually
I feel like fraud
way.
happens so much now.
Dr. Cleveland, you wanted to say something?
go ahead.
It is actually way lower than that. So you are trying to detect a rare event with probability of less than 1%. And if you use a goodness of fit measure like accuracy, you are going to get very, very high accuracy because your rare events are underrepresented. If your model says, okay, just assume that everything is valid and there is no fraud, you will miss a very tiny portion of the cases and you will get a very high accuracy. But if you go to Wells Fargo and you tell them that I have found a fraud detection model I've developed, that's the new terminology out there. I've developed a new fraud detection model with an accuracy of 98%. They're going to kick you out of there because that's not the right way to describe your model's performance. And if you say that, it means that you have no understanding of the problem. So yeah, goodness of fit measures depend really on what you want to do and how you want to present your model. I hope the overall answer that you received from me and Dr. Cleveland was sufficient for your question. So here you can see some references that I used to put together this notebook, and some great reads and some great videos for you to watch if you're interested. And as a question I've asked, which metric to pick? What are the similarities between MAE and RMSE? What are the differences between MAE and RMSE? And do you think it is better to stick with one GOF metric or to use multiple metrics? We kind of answered that question, but I want you to tell me why. Okay, and by this, I'm going to finish my lab session today. Stop sharing my screen. Thank you very much for paying attention. And I'm going to pass the host back to Dr. Cleveland.
I will put myself on, and Nico had a very good lab. He has changed his sleeping position at least 3 times in solidarity with maximum likelihood estimation, ordinary least squares, and goodness of fit. So if you can get all those 3, you can get a good afternoon nap. We will resume on Thursday. Again, more on linear regression type modeling. So in our section, we've put quite a bit of emphasis on these linear modeling. You're going to see these again in other classes, and these are valuable tools. So beating them into your skulls repeatedly is important. You can tell from our way of describing it that I don't think either of us struggle with doing them, but explaining them is hard from time to time, and get comfortable with that, because that's life. If you can plot, do so. Linear regression is stuck in my brain. Oh, and you've changed your name to your new one. Excellent. Do you know what movie that's from?
No, I do not.
If somebody in class can name the movie where Abby Normal comes from, everybody gets an extra point for today. I'll figure out how to code that into Blackboard.
Are you serious? Because it's Young Frankenstein.
Old or young Frankenstein?
Young Frankenstein. With Gene
And
Wilder.
Okay, good. Everyone gets your point. So we all get an extra point for today. So that was when he stole the brain from the lab. Which brain did you get? Abby, somebody. Abby who? Abby Normal. And then the rest of the movie follows. Okay. So good. You did good linear regression on your movie watching. Next, on Thursday, we have yet another visit of linear regression. I think by now you should be comfortable with the idea that the actual performing the regression is pretty darn trivial with our various packages. Interpreting the regression, that's where the work comes in. So with that, I am done for today. I have nothing else. We get done early. That's good, because everybody likes to get done early. Any questions before I disconnect?
Oh, I have a question for Farhang.
Okay.
So, in our last lesson, you're talking about how, like, in research, like, well, not in research, but like how you have to take into account, like, the errors, the distance errors from your best fit line and your data point. Like, in your research, did you really have to go in depth with that kind of stuff?
Well, yes. One part of my research, as I was explaining today, is focusing on classifiers. So classifiers are a different family of predictive models. Now we are working with regression. In regression, you basically go for a continuous point prediction. You say, okay, if at time 2, what will be my speed? That can be 5.6, that can be 10, that can be negative 2.3. In classification, you are basically predicting the probability that based on these inputs, you are going to be in class 1, class 2, class 3, or so on. And yes, analyzing your errors, where they are happening, how big their extent is, comes into play. That's a good part of the discussion.
All right, I was just curious.
Yeah.
All right, everybody. Goodbye.
Take care, everyone. Be safe.
Afternoon.